Views of the Earth from high above are common today. Approximately 6,500 known satellites are currently in orbit, and over 1,000 of them are considered remote sensing platforms, observing the Earth's surface from a variety of altitudes and angles. We are all users of satellite imagery, often before our first cup of morning coffee. The daily weather forecast relies on satellite imagery. The maps we use to travel and commute as well, and news coverage of current events. The Landsat program contributes to this global record of Earth observations, supporting the groundwork of scientists and communities on every continent. But there is something special about Landsat. It's been doing it for over 50 years.
Thrusting outward into space, we gain new perspective on ourselves.
The Landsat mission, conceived of in the 1960s, has been running longer than any other remote sensing program. Inspired by the first views of Earth captured and publicized by NASA, science leaders at the Department of Interior found that an ongoing record of Earth observations could be useful for research and surveying purposes. The idea was simple. Position a satellite in a nearly polar orbit, fixed to the solar angle so that each daytime pass would cross the equator at roughly the same local time, providing a recurring view of the Earth's land surfaces in the late morning when skies are typically clearest. The orbit was originally divided into 251 paths, each one revisited every 18 days.
We can map the world from space, and we can update the maps as the world changes. There is no end to the variety of ways space imagery may help us.
The sensors on each satellite capture the human visible range of the electromagnetic spectrum from red to blue, similar to film and digital cameras. But they also observe infrared wavelengths invisible to our human eyes. Data representing bands of the spectrum are captured line by line and processed into grayscale recordings, which can be combined to create natural-looking views like this, or false-color views like this. The usefulness of a band combination depends on the user and the application. While a natural color combination of red, green, and blue may be the most familiar to our eyes, viewing things in near-infrared bands can reveal the contrast between vegetation, burn scars, and more. Shortwave infrared, able to pass through fog, smoke, and thin clouds, can be used to study special vegetation characteristics, heat footprints, and more. Specialized thermal sensors expose even more of the infrared spectrum shown here, highlighting the heated landscapes of Yellowstone National Park. Though the satellites and sensors have evolved over time, a focus on consistency and reliability has guided the program ever since the launch of Landsat 1 on the 23rd of July, 1972.
Perhaps no new development in space is more significant than this. ERTS, short for Earth, Resources, Technology, Satellite.
And liftoff.
9 Landsat satellites have been launched in partnership with NASA since 1972, grouped here into 4 Landsat generations: Landsat 1 through 3, Landsat 4 and 5, 6 and 7, and 8 and 9. In 1966, the DOI announced its plans for Landsat 1, at the time called ERTS. The satellite's primary sensor, the RBV, used traditional camera lenses and an electron gun to read images from a photoconductive faceplate, similar to television cameras at the time. ERTS also launched with a smaller experimental sensor, the MSS.
My company, when they heard there was interest, gave me $100,000 and said, make a model.
That's a pretty big chunk of change for back then.
It sure was. And we flew the first prototype.
Did you have an aha moment designing the MSS where you knew this was going to be revolutionary using this type of technology from space?
I was really surprised. I think I was as surprised as the users at how valuable the data turned out to be.
Physicist Virginia Norwood and her team interviewed scientists and surveyors to narrow in on the spectral bands most useful for research. They designed the MSS to capture those ranges. The team drove the MSS prototype on a road trip across California to prove its capabilities. Impressed with the results, NASA and USGS agreed to make room for the MSS on Landsat 1, although there was no time to build a final model, so the prototype itself, amazingly, was used. Though the program leaned heavily on the RBV as its primary sensor, its deployment was problematic and its imagery was inferior to that provided by the MSS. It was quickly demoted to secondary sensor as a treasure trove of MSS data continued to roll in. This view of Dallas, Texas was the first cloudless image received. Landsat 1 was an immediate success. Within days, the MSS captured an 81,000-acre fire burning in central Alaska. For the first time ever, scientists and resource management officials were able to see the full extent of damage from the fire in a single image while it was actively burning. Landsat 1 data led to immediate and fundamental changes to practices of the cartographic and geographic communities. Country boundaries were redrawn and entire islands were discovered. Along the coast of Canada, one newly discovered uninhabited island was christened Landsat Island. Imagery was received and processed at the new USGS Aero Center in South Dakota, which would become the hub of the Landsat archive for the next 50 years. Designed to last 1 year, Landsat's maiden satellite exceeded expectations by orbiting over 5 years, capturing more than 100,000 images of approximately 75% of the Earth's land surface. The planning for Landsats 2 and 3 quickly solidified into launches in 3-year increments, 1975 and 1978. Designed essentially as copies of Landsat 1, the 2 new iterations continued to host dual sensors, the RBV and MSS. The RBV captured individual images through optical lenses every 12.5 seconds, while the MSS swept along more like the line scanner in a copy machine. Landsat 3's RBV unit had increased spatial resolution, but its imagery was still used mostly for engineering evaluation purposes. Users of remote sensing data were very interested in the quality and geographic accuracy of MSS imagery. In 1974, the availability of global satellite imagery inspired the LACY program, an early attempt at mapping agricultural land cover to address global wheat shortage issues impacting U.S. farmers.
The United States Department of Agriculture has recently started using Landsat to improve the accuracy of United States crop acreage estimates. Agency officials say that by adding Landsat data to their conventional ground reporting systems, they are now able to get greater accuracy at less cost than by using conventional methods alone.
The first 3 Landsats added a wealth of insights to many areas of science, from forestry and hydrology to cartography, environmental pollution, and more. Landsat 3 data was used by over 400 programs in 31 countries. Groups in Bolivia leaned on Landsat to discover new lithium deposits. Officials in Kenya monitored the relationship between cheetahs and cattle, and engineers in Pakistan studied silt patterns in the data to plan for a new seaport. Global imagery was transmitted to ground receiving stations, then moved to the USGS Aero Center for centralized storage and distribution. Though considered experimental, all 3 early Landsats outlived expectations, wrapping up a decade of Earth observations in 1983. Moving forward, the program status was upgraded to operational. With the change, operational control migrated from NASA to NOAA. The second generation of Landsat was one of great technical innovation, but also one beset by many challenges. Landsat 4 featured a new platform designed with a single solar wing. With a lower altitude, its orbital characteristics also changed. Now divided into 233 paths, Landsat 4's revisit rate increased from every 18 days to every 16 days. RBV technology was officially abandoned. The MSS unit lived on, and a new thematic mapper sensor joined it. The new thematic mapper sensor offered higher spatial resolution and additional spectral bands, including a thermal band. Early technical problems plagued Landsat 4. On day 12, its high-gain antenna failed to deploy, resolved 19 days later. In early 1983, a solar panel failure reduced power to 50%, crippling the satellite's ability to communicate directly with Earth for months, prompting concerns about the overall stability of the satellite. The problems with Landsat 4 and the decommissioning of Landsat 3 accelerated the launch schedule for Landsat 5. Landsat 5 launched less than 2 years after Landsat 4, with a nearly identical design and the same sensors, but it included a few technical fixes developed after previous failures. The story of Landsat 5 is one of resilience and cooperation through some of the program's most difficult times. In 1985, NOAA was directed to transfer the operations of Landsat 4 and 5 to a private company, EOSat. Data management and archive responsibilities would remain with the USGS, but EOSat retained exclusive rights to market and sell the data. Under EOSat's contract, which included plans for Landsat 6 and 7, the cost of data rose significantly, limiting the user audience to essentially the military and large mineral and oil companies. Global data coverage also deteriorated as commercial interests rather than public utility dictated image acquisition, reducing capture areas to only areas where the sale of imagery was likely. In tandem with a number of technical problems over the years, the pace of Landsat 5 observations slowly declined. Nevertheless, throughout its functional lifetime, Landsat 5 contributed massive amounts of data to the user community documenting deforestation, agricultural trends, the Chernobyl disaster, the 2004 Indian Ocean tsunami, Hurricane Katrina, and many other events and observable changes to the Earth's land surfaces. Despite big wins and invaluable data for the remote sensing community, Landsat 5 was nearly the final mission in the program. In 1989, NOAA ordered Landsat 4 and 5 to be shut down. A push from Congress and the National Space Council resulted in emergency partial funding that year, and again in 1990 and 91. By 1992, EOSat was producing and selling a bare minimum of data. It was a bleak time for Landsat, darkened further in 1993 by the launch of Landsat 6, which failed to reach orbit. The program received one final zap of the funding paddles around the same time. The Land Remote Sensing Policy Act of 1992, which called for the construction and launch of Landsat 7 and an off-ramp from the privatization experiment. In those final years of commercial operation, Landsat 5 continued to show signs of aging, yet remained functional. Landsat 5 was a workhorse for the program, contributing over 2.5 million scenes to the archive from over 150,000 orbits. Despite all the challenges and shortcomings, Landsat 5 surpassed its design life of 3 years, nearly tenfold. The Guinness Book of World Records took notice in 2013, making it the world's longest operating Earth observation satellite.
T-minus 3, 2, 1, main engine start, and liftoff of the Delta II rocket with the advanced Landsat 7 spacecraft.
The successful launch of Landsat 7 was applauded globally as relief for Landsat 5, and a welcome lifeline to the program's continuous record. But Landsat 5 wasn't abandoned that year. The two satellites orbited in a staggered pattern for 14 years. Landsat 7's third-generation design was based on Landsat 6's original model. The solar wing and power systems were revamped, and for the first time ever, a Landsat satellite was in orbit with a single sensor, the Enhanced Thematic Mapper Plus. The ETM Plus improved upon Landsat 4 and 5 thematic mappers' thermal resolution and included a new panchromatic band, which captured this portion of the spectrum in 15-meter resolution. Landsat 7 added to the observation record with years of science value, monitoring water quality, glacier recession, fire progression, flooding, invasive species encroachment, population growth, and more. Landsat data by this time was returning to affordable nonprofit rates and was becoming commonplace. Unfortunately, in 2003, Landsat 7's scanline corrector failed. As a result, Landsat 7 imagery after that point contained noticeable wedges of non-data. While the remaining available data were still of value, the SLC failure impacted the overall usability of the imagery. Many users leaned back on Landsat 5 imagery where available on applications where mosaics or synthetically filled imagery were not usable. Despite the SLC failure, Landsat 7's calibration capabilities remain unmatched. Though retired in 2022, Landsat 7 continues to play a role in NASA's OSAM-1 program, exploring robot servicing technologies.
4, 3, 2, 1, 0, and ignition.
Landsat 8 launched in February 2013, allowing Landsat 5 to officially retire a few months later. Landsat 8 is a fourth-generation design carrying two new sensors, the operational land imager and the thermal infrared sensor. With 9 shortwave bands and 2 longwave thermal bands, these sensors cover a solid range of the spectrum. By the time of Landsat 8's launch, all Landsat data had been open to the public at no charge to users. A paradigm shift in policy. The traditional film and tape-based mail delivery approach had been largely replaced by digital access online. User interest in data downloads climbed significantly. With Landsat 8 in orbit and high-quality data being served at no charge to users globally, Landsat was shining. A rapid expansion of science applications included fire observation, permafrost research, desert management, iceberg tracking, volcanic activity, lithium mining, and more. Big ambitious projects like LC-MAP, NLCD, and Landfire thrived in this flood of fresh data. Landsat 9, a near clone of Landsat 8, launched in 2021. Landsat 9 replaced Landsat 7 in orbit, filling in the 8-day revisit pattern with imagery unaffected by Landsat 7's missing data issue. The OLI and TIR sensors complement those aboard Landsat 8. Together, the two satellites are well positioned to capture a new era of Earth observations. 50 years after the first launch, excitement for Landsat's future couldn't be higher. The Landsat satellites perform technological wonders in orbit. Without a global partnership on the ground, the data they collect would never make it to users. From the beginning, data collection and distribution was directed by the AROS Data Center in South Dakota. For 50 years, the USGS teams at AROS served the Landsat program by innovating through generations of technology and science. The archive at AROS is currently home to over 10 million Landsat scenes and growing rapidly. To receive data from the satellites, AROS partners with global ground stations. The current Landsat 8 and 9 ground network consists of 5 receiving stations in 4 countries. These stations downlink science and telemetry data, which eventually make their way to AROS. Ground stations can also upload commands. Further enriching Landsat global partnership is the International Cooperator Network. International cooperators serve their user communities by providing direct access to Landsat data in real time. The network includes 12 active stations from 9 organizations around the world. The USGS meets with the international cooperators twice a year to discuss operational management and technical matters. It's a valuable learning opportunity for every partner involved with Landsat. Together, engineers, scientists, community managers, and users across the globe have been critical to the 50-year success of Landsat. 50 years of teamwork, 50 years of innovation, 50 years of resilience. In 1966, Secretary of the Interior Stuart Udall announced his vision to create a program aimed at gathering facts about the natural resources of the Earth from Earth-orbiting satellites. It was a bold proclamation. It was also an idea that worked and continues to work 50 years on.